Friends, over the last year and a half, I've been making some YouTube shorts, putting them up there, physics demonstrations, things that people usually find interesting. And so here's a compilation of a whole bunch of them put together. Don't forget to like, subscribe, and share. Here's a trick for finding the center of mass and balancing a meter stick. Start with your fingers far apart and just bring them slowly close together. And what'll happen is, as the torque changes, it'll slide on one side and stick on the other, and eventually you'll end up in the middle and it'll be balanced. This even works if you've got some random weights taped in random places on the meter stick. As long as you bring your fingers close together slowly, then it'll end up being balanced on your fingers, and you will have found the center of mass. And I'm connecting and disconnecting to a solenoid, and you can see the compass, which is a magnetism detector, going crazy when I connect it, and then it slows down. In this first demonstration, I'm going to put a magnet on top of a fluid filled with iron filings, and you can see the iron filings responding to the magnetic field of the magnet. Hi folks, doing some electrical work, and want to point out that this circuit and the circuit in the home is a parallel circuit, not a series circuit. So the way this works is that coming out of a wire, there's the ground, and then the white is the neutral, and the black is the live, and the black, all the black lines connect in here. These are the circuit breakers. The white all connect together over here, and then the ground all connect back there into the whole box. And so this is almost like an open battery where you've got the positive side and the negative side. And then what's happening is that when you go to an outlet, it's like you're connecting these two sides. And then every outlet, you're doing that over and over again. And even here, all of these and all of these are connected separately, but all these black ones are connected together. And so it's like creating a ladder that you just connect over and over again in all the different devices in your home. And the white wire, the neutral, is connected to the longer side on an outlet, and this is connected to the shorter side on an outlet. And here's one of those outlets. You can see the white wire going to the long eye on the outlet, and the black wire, the live, going to the short. I haven't finished hooking this up yet, but the ground will go here to the green. This thing is called a galvanometer. Okay, it detects small currents. And here's a coil of wire. So it's kind of like the solenoid, except that instead of it being in the shape of the tube, it's just all together. So a solenoid is this, it's like the tube shape. This is a coil of wire. It's just wrapped up the way you'd wrap up a hose or something like that. And you can see the needle here. Now watch what happens. Notice that as I'm moving the magnet, the needle is moving back and forth. The needle is moving. If I just leave the magnet in here though, is it enough just to have the magnet in there? There's a magnetic field now in the middle of that coil. Is there any current? So here's an aluminum tube, and I've got two slots. One has a magnet in it, the other one doesn't. So the one without the magnet, aluminum is not magnetized by anything, so it's not going to stick. The one without the magnet, you can see how fast it falls to the bottom. It goes right up. But the one with the magnet, what happens is that as it falls, the moving magnet creates an eddy current, electricity, inside the aluminum, and that magnetic field from the current pushes back. So that's what happens. If a wire is in a magnetic field and you put current across it, it makes the wire move. Check this out. So one way of doing a muscle up involves swinging the body, and the purpose of that is physics related. Right? It's to get our momentum going up and to get our center of mass higher. So here's a demonstration. So I start myself swinging so that when my legs come up, my back is going back and my center of mass is already on its way up and is already higher. Notice that I haven't even started bending my arms by this point. So that way now I can start bending my arms just really to pull myself up and over the bar because I've gotten my center of mass higher and I've gotten my upward momentum going simply by the swing. Another thing I learned from this video is that there was a hole in my shirt, but that's fluid mechanics and thermodynamics, which is a different video and not necessary for a muscle up. Did you know that the planets go around the sun not in the shape of a circle, but in the shape of an ellipse, which is kind of like an elongated circle, like this? So one way of making an ellipse is having two fixed points and a string, and then you trace around within the string like this. So that's an ellipse. So every point on the edge of the ellipse is the same total distance between the two foci. So if you take this distance and this distance, they add up to the same amount no matter where you are around the ellipse. If you put the foci closer together, then you end up with a more circular shape of an ellipse. And so while the orbits of the planets are ellipses, they're mostly circular, but not perfectly. here I'm taking some strong neodymium magnets and putting them into the middle. There's a hollowed out core, and you can see what the magnetic field looks like of those. Here's how you test an electric fence using just a blade of grass. You see, the resistance of a resistor depends on the resistivity of the material, the length of the resistor, and the cross-sectional area. So, this blade of grass is a resistor, and what I can do to test the electric fence is to put it on there and get a little bit closer. Let me show you. I want to make sure the electric fence is on each time I use it, because otherwise bears get into my beehives and deer get into my garden. So this is a little tip that an electrician showed me. What I do is, I put the blade of grass on the fence and I reduce the resistance by getting closer and closer, and I can start to feel the shock in my fingers without giving myself the full blast of the electric shock. So this is a honey frame from my hives, and the bees have filled all these cells with honey, and then they put a wax capping on the top. Now, I want to get the honey out. So here's the first thing that I do. I'm going to cut the wax capping off of the cells like this. But even once I've done this, that's not enough to get the honey out. And that leads to the next step, which is the honey spinner. So I put the frame, once all the caps are off, into the honey spinner, and spin it. So we're using centripetal force, along with the idea of inertia, to create the fictional centrifugal force, where the honey, instead of continuing to go around, just moves in a straight line, and there's nothing to hold it in, keeping it moving in a circle. This is a polarizing film, which means that it eliminates all but one angle of light. You can see as I spin it, you can still see the things behind me. Now watch what happens when I put it in front of the screen. Notice that at certain angles, it blocks out all of the light coming from the screen, which means that the light from the screen is polarized. The same thing would happen, by the way, if you have polarized sunglasses. Put them on and turn your head from side to side, or just spin the sunglasses around next time you're looking at a screen. When you take off this piece, that's what's inside. So what are we looking at? Notice that this is one metal piece that comes out. It goes in there, it's connected to both of those screws, and so what we have here is an apparatus to test our ideas about projectile motion. That an object that's dropped, so this thing is spring-loaded, like that, and this one sits on the end, so that when I put this up, this one will just fall straight down, and then this one will be shot off the edge and go that way when I let that go. Then I have this level, and I put this level, and according to our ideas about projectile motion, both objects should hit the table at the same time, even though one is given a horizontal velocity and the other one isn't, because the only thing affecting them, pulling them down vertically, is the acceleration due to gravity, which is the same for both. So let's give it a shot. And now let's see that in slow motion. Two. So here are 2 meter sticks. One has a mass attached low, the other has the mass attached high. The question is, if I were to drop these at the same time, which one would hit the ground first? See what you think, and now we'll test it out. Here's the one with the mass is attached lower because this one has a smaller moment of inertia, and so it's able to accelerate faster. The other one, the moment of inertia is higher, and the torque is about the same, not too different. Not as different as the moment of inertia. Have you ever wondered why a doorknob is shaped this way? Well, when it comes to turning something, the key factor is what's called torque, sort of like turning power. And torque depends on two things: the amount of force you exert, but also how far you are from the center of rotation. If this was something very thin, then you would have to exert a lot of force to generate the same amount of torque. But since this is wide at the edge, you're farther from the turning point, then you don't have to use as much force to generate the same amount of torque. So there's actually some design, physics behind the shape of it. It's not just for the way it looks. Have you ever wondered why doorknobs are on this side of the door and not in the middle or even near the hinges? Well, it's because of what's called torque. Torque is what you could call rotational force. And the farther you are from the hinges, the more torque you have. So if you put the doorknob in the middle of the door, you'd have to generate twice as much force to generate the same amount of torque in order to open the door. So by putting the doorknob at the other end of the door, opposite from the hinges, then you get more torque and you have to exert less force to be able to open the door.